That's okay. I'll give you another window. At that time, you can type in the register number. Now let's get into our business, right? So we have spoken we have learned about the cryptography, encryption, decryption, and then slowly we looked at the message, the hash codes, right? So yesterday we have learned about SHA-512. I'm sure a good number of you have revisited it to understand in detail how SHA-512 is working, what's happening to all the registers, what are the rounds, number of rounds, what's the size of the registers, what are the initial values, how are they changed, and what's the constant key which is given, how the input message is created as different words and they are scheduled for every of the rounds. What's the size of the output message digest which we get through SHA-512, right? So these are the some of the things which we saw yesterday. Now we get into another title, another topic of message authentication code. All right, MAC, message authentication. Um, I'm sure we'll be learning about HMAC and CMAC in our schedule, even if it is not in our syllabus. We'll spend little time to learn about them in the coming days. But for today's class, we'll see a little bit of overview of what a message authentication code is, what are its requirements, how do they exactly differ from our message digest or hash code, or your encryption, right? So that's the objective for today's session. Let's move on. So before getting into that, just to quickly recall, what are all the different attacks which we encounter? Earlier we have seen what kind of attacks, what are the different attacks which can happen on a data. Specifically on the network, what could be the different attacks? All right, one is disclosure of message. What's the instance? What's the example? A release of a message content to any person or process who is not possessing the appropriate cryptographic key. Here, I would like to draw your attention on something called war driving. I remember I have spoken about war driving in the computer networks class. I thought I will talk about this a little more here so that we can understand what disclosure is all about. Right. So when you talk about these, computer networks, especially on the wireless network, 802.11, the Wi-Fi network 802.11i, where anyone which includes the attacker would like to listen to the conversation somebody makes to others is possible, right? We call it as war driving. For instance, we have the Karunya campus. Assume that at every of the peripheral, every of the corners, we have installed the Wi-Fi access point. As you know, the Wi-Fi access point signals are generally in radius form unless they are blocked by any circumstance or any of the buildings or other obstacles. They are going to form a circle. So obviously, when you install a Wi-Fi access point at the corner, it is going to spread its signal outside the campus, outside the compound wall as well, which provides a means of access for anyone to get into the network. For instance, somebody wants to get into KWL, he may not be able to at the initial attempt because his MAC address has to be bound with the DHCP server. Then only he is authenticated. Nevertheless, if he just wants to know the traffic, okay, what is exchanged or who are all in conversation, it is very well possible for anyone if he or she is working in the promiscuous mode. All right, so he can join. As you know, the data at the data link layer and the network layer, they are not encrypted, right? So they are exchanged as the plain text. What is actually encrypted? Normally, the application layer data is encrypted unless you have any special mechanism to encrypt the transport layer protocol and the packets as well. Otherwise, generally, they all are plain text. Assume that in the data link layer, the frames are exchanged between the devices, which contains the source MAC address, the destination MAC address, and other details, right? So what are we going to get out of the source MAC address and destination MAC address? Now, anyone who understands what is the source MAC address and destination MAC address can come to know which manufacturer has produced that network interface card, right? By looking at the first 3 octet or first 24 bits of the source MAC address and the first 24 bits of the destination MAC address, anyone who wants to know the manufacturer, it is possible because you know about the characteristics of MAC address. All right. Now, having that idea is going to give an exposure to the attacker that what are all the vulnerabilities which are available. For instance, any of the manufacturers, when they are preparing, when they are creating such devices, the attackers would normally learn the vulnerabilities or the possible weak areas for attack. Now, the source MAC address has given a way for the attacker to identify what can be done on that particular packet, on that particular network interface card. Now, just analyzing the data, just analyzing the traffic, someone can come to a conclusion that what kind of attack can be established on the particular communication or the network. You should understand that he has not possessed or he has not even cracked the key or the secret message or the password which is used for encryption, but still he will be able to set up the attacker. All right, so this is just an example of disclosure as well as the traffic analysis. All right, so without possessing any key or the password, somebody can learn what kind of attack even be set up on the network. Not only that, you can easily come to a conclusion that who is that person who is conversing. All right, assume that if there is a heavy flow between two specific machines, we can know if you are able to compromise a person internally, you can easily find whose MAC address is that, what kind of message he's conversing among them, the traffic analysis. All right, and then moving on masquerade is, the changes, the it is attack on the integrity of the message, right? So insertion of message into the network, acting as if I am that person, then changing the content modification, sequence modification, generally the replay attacks to confuse the intended receiver, the so-called genuine receiver. Timing modification is going to, delay the message. Probably it can be captured at a particular time. Then by changing the timestamp, the message can be sent across to what, to confuse the receiver. And probably the source and destination repudiation, acting as if I never sent, acting as if I never received that message. All right? So these are the general attacks which are specific to the networks. All right. Now, if you look at the first one and the second one, you can do something to mitigate the such attacks using the encryption decryption algorithms. On the other hand, if you look at the points, probably third, fourth, fifth, sixth, you hardly can do something by using only the cryptography or encryption decryption. So in that case, the authentication plays a major role. So it is good if we have some other mechanism in addition to, or to probably replace the cryptographic algorithms. Brudul, I'm in a call. I'll call you back. Yeah, thank you. Yeah. Moving on, what are all the message authentication functions we can use? There are three things. One is the hash function. You guys have learned a lot about the hash functions, including the session which we had yesterday. What is a hash function? A function that maps a message of any length into a fixed length of hash value, which serves as the authenticator. All right, it doesn't require any more explanation. Moving on, the second one is the message encryption. Okay, the ciphertext of the entire message is working as the authenticator. Is it possible to authenticate a message by using the conventional encryption or the symmetric encryption? Yes, it is possible, as you are going to see in the further slides. The third one is something new, which we are going to deal today. The message authentication code, in short, MAC. It is a function of the message and a secret key. Otherwise, it is very similar to hash. Okay, secret key that produces a fixed length value that serves as the authenticator. All right, so we'll talk about them in detail as we progress. Yeah, how do you think a message encryption can give you confidentiality and authentication? On the screen, we have got the symmetric encryption. nothing difficult or nothing critical for me to explain to you. It is known to you already, but still for the completion check, you got your message here. All right. So this is the plain text available at the source, right? And there is an algorithm, encryption algorithm is running, which encrypts the original message. So encryption algorithm takes the message and a key. This key is shared between the sender as well as receiver. So encryption happens using the key as well as the message to get the ciphertext. So this is the ciphertext C, which is transferred across. All right. Now the question is, it is very simple for someone, for anyone to understand that yes, it is providing the confidentiality. How does it provide confidentiality? Because the message which is encrypted and sent, the ciphertext, can be decrypted only by the key which is used for encryption, because it is a symmetric key encryption. All right, so because it's a symmetric encryption, the key which is exchanged between the sender and the receiver, or the source and the destination in our explanation, can only be used for decryption, so that others, somebody who does not possess this key, cannot decrypt it. All right. Here you are able to achieve confidentiality. But what about authentication? How does it support authentication? Yes, this is something important for us to recall, though we know it already. Now you have got something called a key. All right. Now the key is used for encryption, and the same key, all right, same key is used by the destination to decrypt. All right. Are we able to achieve authentication? Yes. Slowly we are getting into the logic. How do we achieve authentication here? Because the key is shared between A and B only. All right. The message is exchanged between A and E, and the key also is already shared between A and B only. What does it mean? In this world of communication, only A and B know the value called K, the key which is exchanged. All right, how does it provide authentication? Still the question is not solved. How does it provide authentication? Yes, now being a person at the destination, okay, the receiver, he decrypts the message using the same key. And is he able to get some legible text? This is the point we need to understand. By doing this, by decrypting it, will he be, if he is able to get a legible message, then he can understand that the same key has been used for encryption. For let me write some random value, probably network, random bad. Okay, so this is the word network, and let me say this is the plain text. Okay, now I go for a classical or conventional encryption algorithm called Caesar cipher. CAESER or CEASER, I'm always confused. Okay, Caesar cipher I'm using, but with the key value of 1. Okay, so when I use Caesar cipher with the key 1, what will be the ciphertext? So this will become O F U X T S L. Forgive me if I have made any mistake. All right. So this is the output we are getting by applying the Caesar cipher with the key 1 to the plain text called network. Okay, this is the ciphertext which is exchanged. All right. Now this is received by the receiver. Okay, and he uses the K as 1. Okay, and he decrypts it to get the value called network. Now he can convince that yes, he got some legible answer, hence the person who has encrypted is the person called A, because he's the only other person in this planet who knows this secret key other than me. All right, this serves as the authenticator, but this imposes another severe problem, because many a times, if not all the times, many a times the encryption and decryption algorithms are automated. Okay, we are not going to intervene as a human being. You and me are not going to intervene at any step that okay, this has to be converted like this has to be converted like this. No, It's all machine coded, either software based or hardware based implementation is already happening. So having that in practice, how are we going to find out whether you are getting the legible? Let me take the example like this. Instead of this OFUXPSL, he has received a message like this OFUXP. Instead of S, he get T and L. Okay. Now, if you use the key value as 1 to decrypt it, what will be the answer? You will get N E T W O. You will not get R. Okay. What will you get? Yes. I think yes. Forgive me if it is wrong. All right. I do not know whether a word is existing like this. I don't know whether it's a good word or bad word. Forgive me if it is. All right. So you get a word like this when you are decrypting this message. Okay. Now the receiver B gets a message like this NETWOSK. Now there is a little dilemma. Is it a genuine message, or is it the correctly decrypted message, or this is incorrectly decrypted? Because I could not get any meaning from this word. It should give me legible answer, right? So now how are we going to take a call whether it is authenticated, right? So this is the checkpoint which you are facing, or this is the trouble which you are facing in the authentication portion, especially when you go for the symmetric encryption. Hope you have understood what I'm trying to convey to you. All right. So authentication is possible to some level, but if there is a deliberate mistake at the sender side, you are now in a dilemma whether this has been encrypted by the right person or not, because the answer is not legible. Now, how are you going to stop the system in case the sender wants to communicate this word NETWOSK to you? All right, you decrypt it correctly, but you are not able to understand that there is no meaning for it. For instance, now how are you going to convince that you have received it from the right person? He is the only other person having the key, and all these confusions will come into picture. That's the trouble with the authentication we want to take from symmetric encryption. Okay. So that's all about the message encryption using the symmetric key, which also provides the authentication. All right. Whereas in the case of public key encryption, yes, we are able to achieve it. So this is a very generic one. You got the message encrypted using the key. So you got the message using the public key of B, that is encrypted. Okay. Obviously this is person A, this is person B, using the public key. So this can be decrypted only by using the private key of B, okay, to get the message. Okay, this provides the confidentiality, we know that, and we also know that it can give authentication as well. How is it providing authentication and signature? Yes, the sender, okay, this is the person A, this is the person B, and A has to encrypt the message using this private key, and this can be decrypted only by the corresponding public key, which is available with everyone including the attacker, obviously, and this gives only authentication and signature. Okay, how does it provide the signature? Because this message contains, this message has been encrypted by PRA, that is the private key of the sender, private key of the person A, who only possesses it. That is the, no, it provides the authentication as well as signature. All right, moving on, we have got confidentiality and authentication. I'm not going to dwell a long time here because we know about this, but quickly, you got the original message which is encrypted using the private key of A. So message is encrypted using the private key of A, and this can be decrypted only by the public key of A. So this provides authentication. And then this message is encrypted using the public key of B. Only the person B can decrypt it using the private key of B. Hence, it provides the confidentiality. So this combination also is known to us using the public key crypto system. All right. Then comes something called internal and external error control. This is again for the completion sake. All right. So what's happening here by using the encryption? There are two modes. Not very critical to understand, but there are two modes of operation. One is this is called the internal control. This is called the external. This is external, internal error control. What happens? Probably this image helps you to understand it in a better way. You got the original message called plain text available here. That is given to a function. We do not know what that function is. Okay, probably this might be message authentication code, or it could be a hash algorithm, or it could be some function which creates a digest out of it. Maybe SHA-12. Okay, and this comes and these two are appended. Okay, so message and the function through message are appended here, which is sent. All right, and that is encrypted using the secret key which is shared. So what happens? You got your encryption algorithm which uses the key. What does it encrypt? The message which is appended with the function of message. Okay, so that is what happening here. Now at the receiver side, you are supposed to decrypt it to get this message and the function of message appended values. They are taken up. Apply the same function again. You are going to compare it, and then if the results are same, then you are going to say there is no change in the message content. All right. Confidentiality as well for what? For the digest as well as the message. What's happening in the case of external? You guys can easily comprehend this. In the case of external, the encryption is not happening with the whole of the content, but the encryption happens only for the plain text, only for the message. Is that? Yes. You got the message, you got the key, you go for encryption of these two, and then the digest is created by the ciphertext. Okay, so function is applied on the ciphertext. What is C? C is encrypted, the output of the encryption by using K on M. All right, so that is what happening as the output of F. So this is concatenated, or probably this is concatenated to the ciphertext. Okay, so this is the encrypted original message, and then this is the encrypted digest. Okay, so this is applied to the function to get the comparison value, and original message is decrypted using the function. So this is called the external error control. What is the external error control? You don't change the message authentication code, or the digest is not included as part of the ciphertext. That is appended along with the ciphertext. Okay, but earlier that is also included into the ciphertext. Now, what is the point here? The attacker will be able to access the digest which is created out of the ciphertext, but because of the strong and weak collision property, he will not be able to create the original message or a pair of ciphertext which is going to produce the same digest. Okay, so these are the two different modes. There is no advantage or disadvantage, but one advantage I could see is the second one. Encryption algorithm is not overburdened. Why? The encryption algorithm encrypts only the message, but in the earlier case, in the first case, the message and the digest put together and then it is encrypted. For larger messages, when you create digest for every individual block, the encryption algorithm is overburdened. That no, it is going to take a longer time than the second version. Otherwise, in operations principle, there is nothing difference between these two. But in the implementation perspective, first one is so the second one is probably a little better in performance compared to the previous one. Okay, now let's get into our business of message authentication code. We have spoken about the message digest and the encryption. Now we talk about the message authentication code. Probably the lines which are written in the purple gives us an overview or the overall picture of what a message authentication code is. It uses secret key to generate a small fixed size block of data. Okay, it's a fixed size block of data known as checksum or message authentication code. It is not medium access control. That is appended to the message. Okay, so you know what is the checksum? Yes, you are getting it right. Yes, we have already done the calculation of checksum. If you have forgotten, I can help you to recall how do we calculate the TCP checksum. If there are two words, for example, 10101010, and another message, another word 11101110. There is a third word 1100 1100. We know how to calculate the checksum. We used to sum up these two, and then we'll use to sum up these two. If there is any carry, we used to go for wraparound. Then you take one's complement. Okay, that will be your checksum that will be sent across. Do you remember the checksum value, irrespective of the input value, whether you go for 3 word or 5 word or 500 words or 1500 words, the checksum is going to be of 8-bit or 16-bit as per the implementation. Same logic. That is what happened in the medium access code. But in the internet checksum, we don't use any cryptographic calculation. We only add the plain values and then we calculate the message digest or the checksum value. But here we use a secret key to generate the small fixed size block of data. Otherwise, the logic remains same. Okay, so medium access code is calculated by the function called C, whereas in the case of hash, we have used the function called H. Just to differentiate that, we take two things, key and message. If it is encryption, we go for encryption. If it is decryption, we go for decryption. If it is message authentication code or checksum, we go for C, the function called C, which takes two parameters K and M. Okay, where M is the input message, we know that. C is the function for calculation. K is the secret key which is exchanged, and this is your output of message authentication code, which is a fixed size block of data. All right. So how is it working? You hardly find any difference between hash and message authentication code except one. Probably I will talk about that as well. All right. You got the original message that goes to the function called C. C takes two things. One is K and M, and it produces a fixed size code. Let me say MAC. That is appended. So what is happening here? You got the original message appended with the MAC value, which is actually the function and C, the function C of K and M. All right. So these two are given. Everything else same, except that the person should, the people, sender and the receiver must have exchanged the secret key among them. So that's the requirement for you to implement your message authentication code. Okay. So key has to be exchanged. If the key is not present, you got the message. Assume that the key is not present here and here. Then obviously this is going to be your hash. Yes. Right. So how this message authentication and confidentiality is achieved? Simple, sir. Go for a encryption. Very simple, right? So your confidentiality is achieved by encryption. Your authentication is achieved by your message authentication code or checksum calculation. So check the message, go for checksum calculation, append it, encrypt it, then you send it. So what is available in this encrypted message? So this is a function of E, this is K2. What does it encrypt? It encrypts the message which is appended with C of K1 and M. Hope I have written it right. Yeah, this is what here. All right. So encryption of something using the K2. What is that something? It appends two things. What does it append? M on one side and the function of C, which takes two values K1 and M on the other side. Okay. This is what happening here, the whole thing. Now, this is a single entity which is to be decrypted using the key. So whatever key which is used for encryption, which is used here for decryption, yes, this uses symmetric key algorithm. Okay, a symmetric encryption to get the plain text, which is appended with the message digest. But the message digest is create not message digest. Forgive me. The medium message access code, or in other words, checksum. Okay, the checksum value which is calculated using the key and the message. So it uses the same key K1, which is used for the calculation of MAC, right? So this MAC has to be calculated once again. Where is it happening? Yeah, it is calculated once again using the same key. Then you go for the comparison. This here, the authentication is tied to the plain text. Okay. Then is there something called authentication tied with ciphertext? Yes, we are going to see that now. Yeah. Here the authentication is tied to ciphertext. What is that, sir? Simple. Take the message. If you recall the earlier architecture where the message was taken and the MAC was calculated for the message and then it was appended before encryption. But here, the message is encrypted first using the key which is exchanged for encryption and decryption, and then the MAC is calculated for the ciphertext. Okay, here hence the authentication is tied to ciphertext. All right, and then this remaining story is simple. You got the what do we have here? You got the function called C, which takes K1. What does it calculate? It calculates the MAC value for what? The encrypted message. So which takes K2 comma M. Okay, this is what happening here, and that is appended. So these two are appended here, sent across, because they are only appended before encryption, appended after the encryption. You are able to get them as two different parts straight away without decryption. Take that one for decryption to put the original message, but parallelly you also can find out its authentication by calculating the MAC once again and go for the comparison. All right. So can you say in a nutshell, how can you differ? How can you make the difference between these two? Yeah, in symbol, it uses a key for a fixed size code to be calculated, whereas in the case of hash, it does not use the key. Okay, that's a fundamental difference. Moving on. Okay, what is that MAC code, message authentication code versus encryption? Okay, if you want to compare these two, do you find any difference? I don't see any of the difference here. All right, as the character on the screen says, he's a little confused. You got the original message in both the side. I'm talking about MAC here. I'm talking about encryption here. In both the cases, you're having MAC. I'm sorry, original message. Here you have got the key. Here you have got the key. Here you have got the function called C. Here you got the function called encryption. Okay, so this encryption takes the message. Here he uses the key and the message, and you get the ciphertext. Here you get the MAC. Okay, but what is the difference? Both are using the key. Both are using the original message. Both are calculating something. Some functions are applied. What is the fundamental difference? One of the differences, as you could understand, you could recall, if I ask you, you will be able to answer. One of the differences is this MAC produces fixed length output. It produces fixed length, whereas it produces based on, not variable, in fact, based on the input. So based on the size of the input, the size of the ciphertext will vary. But whereas in the case of MAC, the size of the input text does not make big difference. Is that all about? No, there is one more point along with that. The next point is the MAC algorithm need not be reversible. Finally, there are some ways and means for us to breathe. Okay, MAC algorithm need not be reversible as it must be for decryption. Okay, the main difference technically is in the case of decryption, in the case of encryption with the ciphertext, from the ciphertext you should be able to deduce the plain text. Okay, but whereas here from the MAC, it is not mandatory, it is not required for you to reverse and to get the original message. So now probably if I say MAC has got the property of encryption, property of hash. How can I say that? Yeah. What does it take from encryption? It uses the key. Okay. What does it take from hash? It is irreversible. Okay. So probably you can place MAC between the encryption and hash algorithm technically for having a lot of benefits out of it. Okay. Finally, before winding up, why should we go for MAC? All right. There are certain applications which are broadcasting the messages. Okay. Okay, you may have to send the same message to multiple receivers. In that case, is it helpful? Yes. In that case, look at the second point. The authentication can be done through random checking. It is not mandatory as it is in the case of your encryption decryption. For instance, if you are using a public key crypto system, the entire message, every of the message has to be decrypted using the public key of the sender in order to ensure the authenticity. Okay, but whereas here it is not mandatory because the message authentication code which is created or the checksum which is calculated is fixed for all these messages. So it is enough if you take one MAC, find out one MAC, take one of the messages at random, find out the MAC once again, compare these two. If they are same, you need not worry about the other messages as well because they all have produced the same MAC and it is going to be from the same person. So you are able to do the authentication. And the second one, the advantage here is, though it is random checking, the advantage here is you need not check every time whenever it is required. Whenever you feel that there might be some authenticity issue, yes, you can go for this MAC. Whereas, as I have told in support of the first and second point, you need to go for the entire encryption decryption in the case of an cryptography, regular cryptography system for authentication. Okay. The third one, probably on the implementation perspective, the authentication and confidentiality functions can be separated and it gives you some architectural flexibility. Remember our OSA layers, which is having 7 model. Why 7 layers? Why do we have 7 layers? As we know, one of the reasons is the change in one of the layer is not going to affect the functionality or the performance of the other layer. Similar to that, if you could tie up the authentication and confidentiality as it is in the case of public key crypto system, you don't have the flexibility that you have to implement it. But if you could differentiate it, for example, okay, I go for MAC for authentication, I go for the symmetric encryption for crypto system, then you can plan whether you want to implement it or not. If you don't want it, you can remove it. If you don't want it, you can remove it. But in the case of encryption decryption, you need to go for implementation of that. Okay. And this is also again the lightweight one. And MAC does not provide a digital signature. Yeah, that is the downside. Probably I put int mark here. It does not provide digital signature. Why does it not provide digital signature? Because both sender and receiver share the same key. Okay. Please remember, this is the place you can find the difference between digital signature and authentication. Okay. What is that authentication? Authentication, suppose there are two people, A and B are communicating. B can authenticate that it has received it from A, and A can ensure that it has received it from B. If the keys are shared, only the key is used for encryption. What is the digital signature? Suppose A has sent a message to B. B wants to validate the message. He can forward the message to somebody called X. He also should be able to verify the message whether it has been sent by A without exchanging the secret key which is shared between A and B. Okay, so that is called digital signature. Even a third party can verify the signature. That is called digital signature. Because both sender and receiver share the same key, now the third party person cannot find out whether the message is from A or B because both of them have got the key. What is the case of authentication? Authentication is between these two entities. You don't require a third person to authenticate it. All right. We are going to learn something about Kerberos as we progress in the fourth unit. That we'll learn more about the authentication and authenticity and the digital signatures. All right. So probably we'll stop here. In the next class, we'll learn at least one of the MAC algorithm. I'm not sure which is available for our discussion. And then we'll go for the digital signature standards and we'll learn about digital signature algorithm to wind up the third unit. All right, so that's all from me for today. Thank you for listening to me.